So here is the course, the physics of semiconductor devices. Course name is PHODT 4. Okay, so let's start about the actual syllabus, and we are going to start with the first module, that is properties of semiconductor. In that one, initially we'll try to look at the what is meant by the semiconductor and how the materials are classified on the basis of their conductivity, or the its values of the electrical conductivity. Okay, so let's talk about the its classification of the materials on the basis of their electrical conductivity, or on the other side we can talk about its resistivity as well. Okay, so the classification of the materials, we know that the materials are classified on the there are three categories. Probably you everybody must be knowing the things that the materials are classified as insulators and the conductors, and in between there is one more class called as semiconductor. Okay, now how they are classified? Firstly, first answer comes in our mind is nothing but the its electrical conductivity. Okay, so now here it comes that the how its resistivity or the conductivity of that material is varying with respect to the its physical quantity, that is its electrical conductivity, right? As we know that the electrical conductivity of the material whose conductivity lies between the order, that is 10 raised to minus 18 per ohm per meter to 10 raised to minus 8 per ohm per meter. If the conductivity of the material lies within this range, we particularly uh, categorize or the classify that materials into the insulators one. On the other hand, if we go on the other side of the classification of the material or the conductivity, if the material's conductivity is above the 10 raised to minus 3 per ohm per meter, and it is going up to the order of the 10 raised to 18, then such a materials are uh, classified as a conductors one. And apart from that, whose conductivity lies between the minus 8 10 raised to minus 8 to 10 raised to minus 3, and then such a materials are classified as a semiconductor. So this is something like crude, and already we have seen since our maybe junior college, we have seen that the how they are classified, right? So moving little bit ahead, and we will try to uh, understand that the why the insulator has this much low conductivity, and what is exactly difference, as we have just trying to learn these semiconductors at the master level. So what is the another uh, phenomena on which we can categorize the materials in this what we call it as classification of the materials by the another physical phenomenon which we can distinguish or we can categorize? Yes, anyone? Classification of the materials on the basis of the another physical quantity. One of these is the resistivity or the conductivity. Band gap, yeah, exactly right. So what is mean by the band gap? Okay, so what is mean by the band gap? What is mean by band gap? Okay, good. Anyone else? Or the another definition? one shell to the another shell. We can means we can get the other definition as well. Yeah. Some sense it is correct because shells are generally filled, so we can't say that moving the one electron from one shell to the another one. That is the transition of the electron. Yeah. Anyone else? Okay. What happens exactly within the band gap? No. Okay. Let's try to elaborate the. Okay. All right. Yeah. That is actually there are okay various ways we can just try to define the uh, define or the we can just elaborate the things or explain the things what is meant by the band gap, right? So actually what happens, what is meant by the band gap, or why the some materials conduct and some doesn't, right? So we are going to understand that the why these materials are some are conducting, some are insulating, and the some are semiconducting one. Okay, so let's have a little look over the shells, right? This is valence band where the few and there is obviously the valence band is below and the conduction band is above, right? And uh, then what happens that we can just try to have the on the y-axis the relative energy difference is given, okay, and it is for the all the three figures, right? So what happens that in case of the insulators, right, so there are plenty of the electrons are, we can say that the valence band is completely filled, valence band is completely filled, right? And in between the conduction band and the valence band there lies a, at the center is the, what is that EF? EF is nothing but the Fermi energy level, right? It lies at the center of the conduction band and the valence band. And as we know that in case of the insulator, there are electrons are filled. Okay, they are completely filled, and in a valence band is a sorry, in a valence band there are electrons are completely filled, and conduction band is completely empty. There are no electrons are present in the conduction band. So what happens that when we try to excite the electron from the valence band to the conduction band, that doesn't get this much energy, this much barrier. So this barrier is quite high. This barrier is quite high. So when electron gets excited, it doesn't get up to the conduction band, and it falls back to the its valence band itself. And so we can't say, we used to say that okay, that material is insulated, or else the it is not conducting the electricity. Okay. So this difference actually uh, uh, is called as the band gap. Okay, here the electronic wave function doesn't exist. Electronic wave function doesn't exist means particle doesn't exist in between these two bands, right? That's why we call it as band gap, or the electronic transition is not happening here, or it is forbidden by the what we used to say by the rules which are given by the that which rules are given that uh, Pauli's exclusion principle, right? According to which the what we can the electrons are filled up in the shells, and which transitions are can be possible or which are not given by the Hund's rule, right? So this is what the band gap is all about between this conduction band. So this gap is quite high. You might be thinking that uh, gap is very high means we can say is if it is greater than the maybe 3 or 4 row electron hole, then such a materials are called as the insulating materials. Okay. On the other hand, if you look at the semiconductor one, so same scenario is there. Okay, conduction band, valence band, it has the same place, but the difference between the energy level is lesser one. Difference between the energy level is a lesser one. So what happens that in the valence band there is a partially field, and there are few electrons are already present in the conduction band. So this electrons are available for the current conduction. These electrons are available for the current. When we try to supply the energy, obviously these electrons already they are in the conduction band. They are available for the conduction. Also, if this gap is small, and if we supply the energy, obviously we can excite the electrons from the valence band, and they can move into the conduction band, and obviously its conductivity can be increased, right? So this is how the this gap between this semiconductor, or else this gap is small. That's why we can say that it's a partially conducting and partially insulating. If we don't supply any external energy, then obviously this material are acting as a insulator one. They are acting as an insulator. Then you must be thinking that why there are few electrons are excited into the conduction band, or why they are present in the conduction band. That is because of the thermal energy, because of the thermal agitation at the room temperature, right? That's why they are just there are few electrons from the below the valence band. Below the valence band they get available uh, for the, or they get excited towards the conduction band, and these electrons are available for the current conduction. So this difference is a smaller one. It can be lies between the maybe few milli electron volt to the maybe 2 to 3 electron volt. This much band gap is there, but obviously there are few materials whose band gap, or semiconducting material whose band gap is more than 4 electron also. But again we can categorize that as a wide band gap semiconducting material, and the small band gap semi or narrow band gap semiconductor as well. Okay, so now band gap remains the physical quantity remains the same here, but the quantitatively the difference is smaller one. On the other hand, and obviously its conductivity is lies between this is, if we just look at the order is quite high. Is a 10, if we go from the minus 18 to plus 18, that becomes a 10 raised to 36 highest it could be having, right? So on the other hand, we can talk about the conductors. Okay, mostly metals are conductors one. So here that the conduction band and the valence band are overlapped with each other. Okay, so there are we can't distinguish that to one electron is from whether it is from the conduction band or the valence, because they are the overlap. Whereas in some cases that the some metals or the some materials are such that this gap is very small. Gap is a very small, so such materials are also categorized as a conductor one. So there are free electrons. Okay, there are very much free electrons are available for the current conduction. Whenever we just try to supply the energy to it, obviously they just try to carry the current with a very high amount. So that's why we call them as a conductor. Okay, so now uh, let's talk about the crystal structure. Obviously, this when this current conduction is happening, we must talk about the crystalline nature of the material, whether it is amorphous or it is crystalline. So, let's talk a little bit about the crystal structure. We are talking about the properties of the semiconductor, right? So, one of the thing is the crystal structure. As we can see that there are many important semiconductors who exist have a diamond or the zinc blende lattice structure. So these are the lattice structures, huh? Not the crystal structures I am talking about. So many of the semiconductors have either the diamond structure, diamond lattice structure, or the zinc blende lattice structure. We'll understand in a moment that what is the diamond structure, lattice structure, and the zinc blende structure in a moment later. Okay, so which belong to the tetrahedral phases. Okay, tetrahedral phases. Let's see. Okay, so now each atom which is surrounded by the four equidistant nearest neighbors which lie at the corners of the tetrahedron. So what is the tetrahedron phase here? That is the each atom which is surrounded by the four equidistant nearest neighbors which lie at the corners of the tetrahedron. Okay. Now the diamond and the zinc lattices can be considered as a two interpenetrating FCC structures. Two interpenetrating like lattices, or the what we can say, the one FCC structure. We know that the most interesting thing is that the one FCC structure, we know that the 8 atoms on the corner and the 6 atoms are on the each faces of that cube. So now within that unit cell there is a one more FCC structure which is interfaced, okay, or interpenetrated. So that we are going to see in case of the diamond lattice or the zinc flint lattices here. Now for the diamond lattice, all the atoms are the same, right? So diamond is made up of the carbon atoms, right? So the in that case all the atoms are of the same kind. Whereas in case of the zinc blende lattice, one sublattice is of the one atom and the other sublattice is of the another kind. Means something like example I can give is the zinc oxide, right? So one of the atom is a zinc and the other atom is a oxygen one. So they are composing or they are trying to form the zinc blende lattices. We will try to picture out what is the these lattices in a moment later. Okay. Now, if we look at the periodic table of the elements, then the most of the 3 and the 5 group compounds crystallize in the zinc blende structure. Okay, when we just try to look at the third group and the fifth group. Okay, obviously 5, 3 and 5, because its octet should get completed. Octet should get completed. So compound crystallizes in the zinc blende structure. However, the many semiconductors, SC stands for the semiconductor, including the few, some of the from the 3,5 compound crystallize in a rock salt or the Woodside structure. Woodside structure is of the what we can say is a zinc oxide structure. Okay, and rock salt is something like the other one, like salty means NaCl. Okay, now okay, I was the crystal structure of the diamond, right? So the example for the crystal structure of this semiconducting material is one of the example is the diamond lattice. Diamond lattice is in the sense that the there is a phase where the tetrahedron, where the lattice is composed of the similar kind of the atoms, similar kind of the carbon or as a silicon or as the germanium. So such a materials we call it as a diamond lattices. Okay. On the other hand, uh, in case of the zinc blende crystal, the structure of the gallium arsenide or the indium phosphide is the example. Now you can clearly distinguish between the diamond lattice and the zinc blende lattices. Okay, here you can see the yellow atoms which are surrounded by the four nearest neighbors which are nearby its what you can say, one of the atom is on the corner and the remaining 3 are on the nearest faces of the particular that crystal structure. Okay, you can see over here the similar structure is there, but the thing is that the atoms are of the same kind on the left hand side of the figure. On the right hand side you can see over here the atoms are of the different kind and they are composing the zinc blende crystal. Okay, and the left one has the diamond lattice where the atoms are of the okay. Now, yeah, okay, so now you can look at the this crystal structures and periodic table of this elements, right? So here we are having the fourth group elements, right? Apart from the carbon, it's silicon, germanium, then tin, Pb, and then the Fl. These are the elements. They are called as the elemental semiconductors. Why? Because they individually, the particular element is of the semiconducting behavior or semiconductor property they possess. Why? Because their octet is half filled. partial half filled in the sense that they are acting as a semiconductor itself. Their octet is half filled, means the 4 electrons are filled and 4 electrons are empty one. Okay. On the other hand, what we can have here is nothing but the group 3 and the group 5, so that their octet gets completed. So these elements or these group elements, if you combine them together and forming the semiconductors, are called as the compound semiconductor. Also, the other combinations, if we make such as the suppose the second and the sixth one, okay, second and the sixth group elements, if we combine, then we can form the another kind of the semiconducting material, also known as the compound semi. Okay, now you can see this screen. Okay, so now, if you look at this, the column 4 semiconductors, that is silicon and the germanium, are called as the elemental semiconductors, right? As already we have seen on the previous slides. Next is the two elements. If we just try to combine together, then we call it as a binary semiconductors. Okay, group 3. If we choose the one of the element from the group 3 and the one of the another element from the group 5, and if we combine them and form a particular material, then such a type of the compounds, such as the gallium uh, nitride, gallium phosphide, and gallium arsenide, are the semiconducting, or they are forming the semiconducting materials, and they are commonly used in the LEDs, right? So when we try to form or form the material, the compound, by using the group 3 element and the group 5 element, then so the forming compound is generally used in the light emitting diodes, so that we can get the light emitting diodes in the sense that their emission is in the visible region. So they are mostly useful in forming the diodes one, okay? LEDs. Okay. Now there is a possibility that we can form the ternary kind of the compounds, or the quaternary as well, right? We can make the combination or choose the combination of the materials such that it completes its octet, and it can act as a semiconducting material. So what we should have the primary condition, it should complete its octet, as well as it should show the semiconducting properties. So three element compounds such as the gallium arsenic phosphide, and the 4 element compounds, that are quaternary compounds, such as the indium gallium arsenide phosphide, can be grown to provide the added flexibility. So depending upon our requirement, if we need the LEDs, we should choose the material from the 3 and 5 groups, and if we know the if you require to have the added flexibility in choosing the material products or material properties, need some flexibility in the material, then obviously we must choose such a materials that from the quaternary or the ternary compounds to get this particular property of the appliances. Okay. Now if we require the fluorescent materials in some applications, then they used generally in the television screens. So they are chosen from the second and the sixth group compounds. Okay, such a semiconductor as ZNS. Zinc sulfide is the one of the material, and where you can get the fluorescent material from the group 3, group 2 and the group 6 uh, material we can, or element we can choose. Now, one of the most characteristic of the semiconductor, which distinguishes it from the metals and insulator, is its energy band gap. So on the basis of the energy band gap only, we distinguishes these materials from the metals and the. When we have started about the crystal structures, I said that there is a difference in the diamond lattice and the zinc plane lattice. So let's try to understand that what is exactly happening over there. Okay, so silicon has a two interpenetrating FCC structures with the 8 atoms in these positions, and the diamond lattice arrangement in the unit cell. Let's try to look at this how it is formed. Okay. If we look at the corner atoms, they are represented as from the FCC structure I am just talking about, single FCC, okay, and then we will interpret the another one and how it is interpreted into that, interpenetrated into the previous FCC structure. That is the first uh, element. First element or the corner atoms can be at the 0 0 positions, and the face centered atoms can be placed at the half half 0 half 0 half and the 0 half half. You might be aware of the things, right, in the FCC structure, right? So face centered atoms are situated on this mm, uh, positions as the half half 0, means this is something like xy plane where z is 0. Wherever the that coordinate is 0, that plane that position is missing. So the next atom is on the xz plane, and the last atom can be on the y and z plane. Okay, so these are the face centered atoms which are placed on this uh, particular unit cell. Okay, means obviously there will be the above. You must be thinking that there are 6 faces, and why you have shown only the 3 positions of the face centered atoms. If we choose the corner atom as a 0 0, from that there is a obviously exactly above there is a one more face is there, so we have to choose only the uh, one particular face, because that comes on by after the translation only. Okay, on the other hand, the another within the same material there is another interpenetrating FCC is there, and where it is placed, the instead of corner atoms, instead of this corner atoms, the first atom will be situated at the 1 4 1 4 1 4 position. So next to the origin, next to the origin at the position of the 1 4 1 4 1 4, the one atom will be placed, and obviously in succession with this they are translated, each atom will be translated by the 1 4 position, 1 4 position, and we will be getting the another unit cell within the itself. So here is the crystal structure of the diamond lattice, we would say here, right? So now you see I have shown the face centered atoms with the red atoms, and the interpenetrated atoms with the green atoms. So you can see over here the green atoms at the bottom on the left hand side. So this will be connected to the 3 uh, face centered atoms nearest to it is one is on the left hand side, one is towards the bottom, and the one is which is facing the face which is facing to us, our outer face. So this is how it is connected, and the nearest corner atom is the which is the uh, uh, on the front side left, is the one of that. So this is first green atom is connected with the these 4 atoms. Okay, now the position of this atom is at the 1 4 1 4 1 4, and similarly other atoms positions can be seen in case of the this diamond lattices. Okay, so next. Okay, now we'll try to understand that the zinc blende lattices, or the atomic arrangements in case of the zinc blende unit cell. Okay, one of the example for this is the gallium arsenide, has a 2 interpenetrating FCC structure. Now what is the difference with the earlier structures? In case of there was a atoms are of the same kind. In case of this zinc blende structure, atoms are of the different kind. Okay, I have shown in the previous diagram to understand the different atoms position. That's why I have shown them with the different colors. Don't get confused. In case of the diamond lattice, their atoms are of the same kind. They are not the different one. To show the positions, I have shown them with the different colors. Now in a zinc blende atomic arrangement in a unit cell, the obviously again the first FCC with the usual atomic positions. Okay, now we can say the gallium atoms are the situating at the corner as well as on the face center, first one, and the next within the unit cell there are arsenic atoms, and their positions are give with the interpenetrated FCC has been shown over here. Their positions you can find over here. You see over here that the uh, these are the different kinds, okay, different kinds of the atoms are there. So on the face, red as well as the uh, light light green colors are of the related to the one FCC structure, and the uh, dark green atoms are corresponding to the arsenic one. Dark green are corresponding to the arsenic one, and the red as well as the light green are related to the gallium kind of the atoms are there. Okay. Now, now here we can understand the tetrahedral position in the unit cell in the following figure. In case of the silicon unit cell, in which all atoms are of the same type. Okay. So we can see the this is a kind of the diamond lattice one. Okay. Which is a tetrahedral position in the unit cell. In case of the gallium arsenate unit cell, in which the atoms are of the two different kinds and they are connected by this way. So you can clearly understand that the what is the difference between the diamond lattice and the zinc plane lattices. Okay, on the left hand side, see how the atom is connected with the other atoms, and in case of the gallium arsenide, how the atom is connected with the other atoms. This is which is all related to the what we can say is the semiconducting properties of the material. This is the crystal structure and how we can now form these semiconductors or classify the semiconductors on the basis of the its resistivity and or else the conductivity as well. All right, so thank you.